Hi everyone. Now, it's time for the inverse Laplace transform. And really, the whole point of the inverse Laplace transform is, we're obviously going to the S domain. But up until now, we haven't really been doing anything with it. We're just getting there and showing that we can get there and what it kind of looks like to get there, right? The whole point of this is that we want to use the forward and inverse Laplace transform to allow us to solve differential equations in this class. And in particular, we want to solve constant coefficient nth order, so whether it's second, third, fourth order, doesn't matter, linear IVPs. And so that's what this is used for. So just quick notation, if Laplace of f of t is equal to big F of s, then the inverse Laplace transform is just the Laplace with a minus 1 exponent in it. F of s is equal to f of t, which kind of makes sense. And so, just to put you at ease, every Laplace transform in the S domain is going to correspond one-to-one to a function f of t in the t domain, in the time domain. So as you're solving this, if you think you're getting too creative or that you're not sure which property to employ, as long as you're not breaking any rules, it's fine. They one-to-one correspond. So whatever you're doing will lead to the right answer, assuming everything that you're doing is correct. It's okay to get creative. And then I also want to implore you to, from now on, use table 5.3.1, which is the Laplace table for this course. No more trying to do these using the integral or, no more using the integral. Just look it up for whatever function you need. Have it side by side while you do these problems. And the main understanding is how do you manipulate the properties, how do you factor stuff, how do you complete the square, how do you do partial fractions, all these skills that we'll get to in this video. So stay tuned. Let's do this example real quick. And as you notice, I haven't given you any tips or any methods on how to do these because it's really going to be, you have to kind of just look at it and determine what you think is your best course of action. And so for this first one, we have 6 over s plus 2 to the 4. Okay, we have s plus 2 in the bottom, right? Which makes me believe that my Laplace is going to have some exponent shift, right? It has some exponent shift in the time domain. And so the way that I like to write this is, so now it's going to be Laplace, inverse Laplace of 6 over s to the 4, and I'm going to multiply it by the exponential that would cause it to be like that, which is minus 2t, right? And that should make sense. It's basically just when you go from the inverse, from the forward Laplace transform now to the inverse, everything is one-to-one. So because this worked going to the S domain, it's going to work going back. And so now what the issue at hand is, okay, Laplace, inverse Laplace of 6 to the s, 6 over s to the 4. Let's think about this. The polynomials, remember the t? What was the Laplace of t cubed? It would have been 3 factorial over s to the 3 plus 1. 3 factorial is equal to 6. S to the 3 plus 1 is 4, which is exactly what this is. Therefore, this whole thing is just t cubed e to the minus 2t. And that's it. Pretty basic one, for starters. And then, yeah, so because the inverse Laplace transform is one-to-one with the regular Laplace transform, and they won't mention this in this class, and they won't ever show you, but the inverse Laplace transform is actually also an integral transform. And so, due to my argument in, what was it, the first video? Yeah, first or second video of this unit, therefore, the inverse Laplace transform is also a linear transformation. So it follows the same rules of inverse Laplace of c1 f1 of s plus c2 f2 of s is going to equal to c1 Laplace of f1 of s plus c2 inverse Laplace of f2 of s. Oh, I think I forgot a negative 1 here. But good thing I'm catching it now. Obviously, you can't take a Laplace of already something that's in the S domain. And that's equal to c1 f1 of t plus c2 f2 of t. And you don't need to say where it exists on the time domain, but if you want to be sure, just say it exists from t greater than 0. And it should be good to go. Great, so now let's try to see this in action, right? So we have this problem here. 6 over s plus 3 to the 4 plus 3 over s squared plus 9 plus 2 s plus 2 over s squared plus 4s plus 13. Now, the first one looks kind of like what we just did. The second one looks like a sine of 3t, probably. And then the third one is where, okay, what do we do here, right? So let's tackle this one by one, right? Because of linearity, we can do this separately. So this is going to be e to the minus 3t, right, of the inverse Laplace of 6 over s to the 4, which we just proved up there that was t cubed. So this whole thing is just t cubed e to the minus 3t. That's good. Here, let's just go down. This is exactly what's on the Laplace table for sine. A over s squared plus a squared, where our a in this case is going to be 3. So this is going to be a plus sine of 3t. And then this one is the one that's tricky. So the s plus 2 in the numerator hopefully gives you some hints on what to do. So first off, let's take out the 2. 2 inverse Laplace of s plus 2 over, okay, obviously the denominator is not looking too hot, so we need to find a way to fix it. This is when you start using completing the square. So what that means is, if we do s plus 2 squared, that's going to yield s squared plus 4s plus 4, right? We have s squared plus 4s plus 13, which means that over here this is going to be plus, and I know where this is going, so I'm going to go ahead and say plus 3 squared, right? The two expressions are equivalent, which means that this then becomes 2. Everywhere where we see an s plus 2. Therefore, we can take out an e to the minus 2t, right? And then this becomes inverse Laplace of s over s squared plus, I guess I can write 9 now. And that is just cosine 3t, right? Therefore, to add it down here, this is just 2 e to the minus 2t times cosine 3t. And there you go. That's the inverse Laplace of that guy right there. So cool. It just comes down to cleverly manipulating these ways into something that you can work with. We're not going to give you a function that you haven't seen before, you haven't taken the Laplace of before, so you know it's going to be something that's either, as of for right now, it's going to be polynomials, exponentials, sinusoids, and so yeah, try to make them kind of like what we did right here. Sorry, and massage it in a way that we get something that's easy to work with. Cool. Alright, this is pretty important. And I know it hasn't been obvious yet because we haven't solved diffie-qs with these, but your success from here on out in this chapter heavily stems from your ability to do partial fractions. And partial fraction decomposition is obviously just changing some rational function, whether it be some f of s over g of s, into something that's more easily that the denominator is split up so that you can take these Laplace transforms a lot easier. And so to practice, let's just find the partial decomp of 3s minus 40 is over s plus 3 s minus 4. Now, hopefully you already know what this means, but just in case, I'll go through it probably just this once fully on what to do. Okay, so what this means is we would love if we could separate the bottom two factors by themselves. And so the way to do this is there's rules with how you pick what goes on top. So if this is a linear term on the bottom, s plus 3, or yeah, if it's s plus whatever number, then the top is going to be a constant. If it's s squared plus 7, let's say, or plus 9, that is what's called an irreducible fraction, and therefore you put an as plus b, or a bs plus c, whatever it may be. For right now, let's just focus on this. If we multiply both sides by s plus 3, s minus 4, then what happens is we get 3s minus 40 is equal to a times s minus 4 plus b s plus 3, right? And the whole goal is to find out what A and B are. That's pretty straightforward to do. And the method I like to use with this, because it's fairly obvious here, is to just let S be very convenient values, right? So, for this first one, let's say we want to let S equal 4. So on the left-hand side, it's going to be 12 minus 40, which is minus 28. If we let S equal 4, that means that this A part goes away. So it's going to be equal to B times 4 plus 3, which is 7. Therefore, my B is actually equal to minus 4, which is good. And then if we let S equal 3 or minus 3 this time, then the left-hand side becomes negative 49 is equal to, at this point, the B part goes away. So we have A minus 3 minus 4 is giving me minus 7. Therefore, in this case, A is equal to 7. And so, what this means is that 3s minus 40 over s plus 3 s minus 4 is equivalent to 7 over s plus 3 plus minus 4 over s minus 4. And that's the whole goal with these. We prefer this, the right-hand side, as referred to the left-hand side, because it makes it easier to deal with, right? Great. Alright, let's go over these little important notes right here. So this is what I was talking about. Well, not the first one, but let's go ahead and talk about the first one. You're going to see sometimes s plus 2 squared, or some linear term quantity squared. And a lot of my students ask me, okay, they understand that we need this, and they even understand that we need this. What they sometimes don't understand is what goes on top of this one. It's just a constant on top. Because if you think about it, the for s plus 2 squared, for s plus 2, all you would do, like if we only had s plus 2 as over here, we would make it a constant, right? Our guess would be a over s plus 2, right? Now let's say we squared that. If we just square a constant, we still get a constant, which is why on top of here we have a constant and not a bs plus c, which a lot of my students like to, at least in the beginning, think, oh, right, because there's a squared over here, and this can't be reduced, allegedly. It should be bs plus c, but that's not the case, and so I want to make that very clear now to, alleviate some pain and suffering that you might have later while you're solving these problems. I hope not, but a lot of people get frustrated with these at times. And then the second one is what I was talking about. This s squared plus 4 yields complex roots, right? And so that's what's called irreducible irreducible factor. And so that's when you have this bs plus c on top. That's the only case when you do. And then this s plus 5, obviously, it's just a constant on top. So as long as you have these two clear, everything should be good to go. Now, okay, this one is long, and I made it long on purpose to illustrate to you how good you have to be at partial fractions to do this sort of stuff. So let's get down to it. So we have 2 times s cubed minus 2s squared plus 8, and then on the bottom we have s squared times quantity s minus 2 times quantity s plus 2. Okay, and we want to take the inverse Laplace of this. So, I can't take the inverse Laplace of this just as it looks right now. So, and I just made a whole little speech about partial fractions, so it's more than likely that we need to take partial fractions, right? Good. Let's go ahead and rewrite this. As in, let's just put the 2 outside for now. And then let's just consider this s cubed minus 2s squared plus 8 over s squared s minus 2 s plus 2. Okay, let's split this up. Let's pretend the 2 isn't there, because really it's irrelevant. We can multiply everything by 2 later. The s squared term is going to have an s and an s squared, right? And based on what I told you up above, over here is going to be an a, and because this is just essentially the squared version of the a over s, this is going to be a b. It's not bs plus c, right? S minus 2 is a linear term, so it's just going to be plus c s minus 2. And then s plus 2 is very similar, plus d s plus 2. And so our goal is to solve for a, b, c, and d. So let's get to it. All you have to do is multiply both sides by s squared, s minus 2, s plus 2. And again, for right now, I'm going to ignore the 2. Okay? We'll add it in later. So I hope I don't see any comments of, Sebastian, you forgot the 2. Your answer is wrong. No, I will multiply by 2, I promise. Okay? Cool. So as you multiply this out, you will get something that looks like s cubed minus 2s squared plus 8 is equal to, okay, a, because we multiply by what's on the bottom, it's going to yield s times s minus 2. Yeah, I don't want it to look that weird. Okay, s minus 2 and then s plus 2, right? We're going to have plus b. Since we're multiplying by s squared, there's not going to be an s. There's going to be an s minus 2, however, and an s plus 2. C, we're going to have a plus c, and we're going to have s squared and just an s plus 2. And then we're going to have a plus d times s squared times s minus 2. Okay, sounds good to me. So from here, what we want to do now is to expand the right-hand side. Okay, and that might seem counterintuitive, but it will help us, I promise, as we solve this. So the right-hand side, if we now just focus on the right-hand side, this term right here is going to yield a times s cubed minus 4s. Okay, that's good. Plus b times s minus 2, s plus 2, that yields s squared minus 4, plus c, this part yields s cubed plus 2s, and then for d, this yields s cubed minus 2s, right? Minus 2s squared, sorry, for both of these. Good. And then, I don't know if you guys have seen this trick before, but you basically just want to get the factors in front of each individual s cubed, s squared, and s together in order to try to solve for stuff like this. So therefore, for s cubed, we have a contribution from a, we have a contribution from c, and a contribution from d. Okay. Plus s squared, where do we have contributions? We have b plus 2c minus 2d. Okay. Plus s, where do we have a contribution from s? We have it from minus 4a. Okay, and then for constants, we just have minus 4b. Now, remember what all this is equal to. This is all equal to s cubed minus 2s squared plus 8. Okay. All you have to do from here is match coefficients, right? So what this is saying is that a plus c plus d has to equal the coefficient in front of the s cubed on now this right-hand side, which is equal to 1. Equivalently, b plus 2c minus 2d has to equal what's on the right-hand side for the s squared, which is equal to minus 2. For s, that means minus 4a. There is no s on the right-hand side, which means that it has to be equal to 0. And then, let's scroll down a little bit, minus 4b, right, by itself has to equal that constant term, 8. Great, so these bottom two are fairly obvious. This means that a is equal to 0, And this one means that b is equal to -2. Let me make this a little bit better. Okay, good. We solved for the first two. And then combining those into these top two equations, which are a little bit more involved, implies that c plus d is equal to 1. And on the second one, it's 2c minus 2d is equal to 0. Right? Therefore, you can solve this out. C is equal to D is equal to 1/2. Good. So our partial fractions are complete, which is good. So s cubed minus 2s squared plus 8 over s squared s minus 2 s plus 2 is going to be, okay, a was equal to 0, so it's 0 over s, so we don't care, right? B was equal to -2, so it's -2 over s squared. C and D were both 1/2 apiece, so it's plus 1/2 over s minus 2 plus 1/2 over s plus 2. Now, remember the times 2. Told you I wouldn't forget. So this means change all of these, just multiply them by 2. So this is 4, that's a 1, and that's a 1. So I'll write a little bit clearer for you. -4 s squared plus 1 s minus 2 plus 1 s plus 2. These are fairly simple to take inverse Laplace of, right? Cool. So this one, remember, inverse Laplace of 1 over s squared was just t. So if we multiply that by -4, that's just -4t. These are both exponents, right? 1 over s minus 2 yields e to the minus 2t, and similarly 1 over s plus 2 is going to yield e to the positive 2t. And so this is what our f of t is from the inverse of what we just did. So great. Clearly, this is not going to be the last time you see partial fractions. Be sure you know what I just did. Practice it a lot. It is going to come down to organization. It's going to come down, it may or may not come down to simple mistakes, but that's ultimately on you and how much you practice. Awesome. Alright. To me, the next section is kind of the culmination of this whole class, in my opinion. It's solving diffie-q's with Laplace transforms. You can kind of do it by yourself now. I mean, you have the tools. You may not know the process, but a little bit of intuition should get you there. But yeah, that's the next section. So, see you then.